Oh, it
Okay,
started.
it started indeed. So, yeah, thank you very much for inviting me to talk about uh, our work about compiling pattern matching to in-place trend modifications. This is a work that we research with Laure Gonnord and Gabriel Radanne. And first, I just wanted to show you our starting point. So can you go to the next slide, please? Um, yes, so that just first a quick presentation of our team. What does it do? Uh, we're the cache team, so that's compilation, analysis, software, and hardware. The scope is quite broad, and we are interested in both verification of programs and also trying to um, extract the parallelism from programs in order to generate some code. And so we have quite a broad range because we start from analysis and abstract interpretation, and some people of the team are working on FPGAs and generating circuits. Next slide, please. Thanks. So for this talk, our starting point was that with low-level languages such as C on the left, um, you can represent data structures the way you like and do modification freely with no real limitations. So here, for example, the mirror function is just copying a pointer, and both are the same in memory after. So we can tweak whatever we want to gain performance. But in higher level languages, uh, where there is a domain-specific language to describe the types, the internal representation of the types is fixed, and we don't have any control over them. And especially in high-level language, functional high-level language, the type are immutable, and when you perform transformation of them, you are reallocating nodes, and you can't tweak the memory layout. So can you go to the next slide? We want to keep the domain specific language to express those types, but we want to keep mutable semantics when we perform transformation. Next slide. So in the first part, we will be interested in our small language to express those structural transformations. Next slide. So this small language is able to express algebraic data types, but there are some restrictions. That is, there is no sharing. We don't want any mutual recursion between types. All constructor slots might have a bounded side at compilation. So if you wanted to have something like a list or something, you can't. And all constructors are of finite arity. And this domain-specific language is used to describe structural transformation through pattern matching. Next slide. So the example that we will use all along this talk is this one. So you can imagine that on the right, that's a view on memory, and on the left, it's the same view on the memory, but once we've done the transformation, which takes the right left subtree and overwrite it over the previous tree. Next slide. Thanks. So just to be clear, we store those types in arrays. So here for a simple tree type, we store it in an array this way. So this is breadth first layout. So we are taking 1, 2, 3, 4, 5, 6, 7 in this order. But we could choose another order to store in an array. The only restriction is that we want to be able, given a node, to find the index of its children easily. Next slide. And for example, if we have multiple constructors with a different arity, in this representation, for example, we are, in order to keep the regularity of the memory layout, we are considering that node 2 is kind of like node 3, and it has an empty slot instead of That is that if we use this representation, we will have dummy cells when we have multiple constructors, and we won't be able to do much to optimize those cells. Next slide. So here, back to the running example, we are back to a single tree, and we want to express the pull-up transformation with this DSL, which is a collection of rewrite rules. So next slide. Here we are interested in the left children of the node, and we and we want to rewrite it to the other one. Next slide. So that in the end we only have this. So the part with node AI, node BTC is completely rewritten in the memory by its right children, which is node BGC. Next slide, please. So that's just our notation to denote the locations. So the location epsilon denote nothing. There's no path. So we still have the entire tree. Next slide. Here with this notation .1 int, you see that 1 is the first children of node, because 3 is the 0th children. And we keep the type because we need to know the representation in memory of the field. Next slide. So, and if we go 0, 3, we are having the tree 2, 4, 5. Next slide. And we can compose those paths. So 0, 0, 3, we only have 4. Next slide. And we can select the int by adding one int to 0, 3 done twice. Next slide. And we can indeed do the same for the other direction. Next slide, please. Thank you. So here I just wanted to show all the memory movements happen. And so next slide. We can see that the node A won't be in the final tree, so we can just discard it. And next slide, I, that's the same for I. Next slide. And now that the interesting cases, the node B will move from its position, which is A1, to the blue triangle. And that is totally possible because there is enough room for in the blue triangle to accept the orange triangle. Next slide. And this is the same for the integer, which is stored in the node. Next slide. But when we try to move the subtree, which is named A2, we can't directly because one part of A2 will go on the red circle. That's because we are moving the subtree up. And we will be able to transfer partly A2 to A1, but a lot of the memory movements are some part of A2 to some other part of A2, and so there are conflicts, and we can't express them at this level of details. So we'll need to be more precise to express this movement. Next slide. So in order to be more precise in those movements, we subdivide the array into layers that will correspond here in the, since we are mostly basing everything on the depth first layer, the breadth first layer, that's not at a distance of 0 of the root, of 1 of the root, of 2 of the root, of 3 of the root. So the first layer has only one element. The second layer, A1, has 2 elements. A2 has 4, and so on. And so we can see the array as kind of this triangle where we have different layers. But it's not really a triangle because the number of elements increase exponentially. So the border are not straight. Next slide. So here I want to explain what happens now that we have layers. We can go pretty fast on this slide because the only thing that change is that you can see that after the path, we have those phi, and those phi means a layer, and k means all layers, 4 layers below this path. So next slide. Here, A and all its layers, so what is below 0, 3, can be removed. Next slide. That's the same for .1 int. Next slide. We have no problem again for B, E, because A will be completely rewritten, so there is no problem. And you can go next slide 2 times, I think. Yeah, thank you. And now we can address the case with the C subtree. So you can imagine that the picture on the left has been unfolded many times, and each time we unfold C, we are losing a layer. For example, here, if we continue, it will be C0, for example, it will be D0, D1, D2, but there will be one layer less than C, because we are going deeper into the tree. Next slide. So the first rule means that the integers in the node can go up along the line which is highlighted, and this can be seen on the rule because there is 2 k2 plus 2 that is written to sent to 2 k2 plus 1, that is each integer move one step up. Next slide. And you can see the same happens for the layers. So you will have C0 which that will come to the circle node just above. One part of C1 will come to B0, and the other value of C1 will come to C0, and so on. Next slide. So at this point, we can see that we have a lot of, we have decomposed the transformation into memory movements that have to happen in memory, and we want to schedule them so that the movement are done as efficiently as possible. So first, we need to understand the interdependence between those movements. Next slide, please. So this is just a recapitulation on the notation used for path, and the fact that we will use the length of path somewhere later, but you should only remember the notation with bar path bar, that is the length of the path. Next slide. And we are interested in the domain of a move, that is we want to have a graphical representation of the domain where the moves are to kind of know which one needs to be done before. And the domain of a node is the domain where it is valid. That is, its date, it's the source memory location and the destination memory location are both within the tree. And since we only have linear equalities here, we will get polyhedron when we plot the domain of the moves. I know that at this point it's not really clear, but next slide it should become a bit clearer technically. Yes, here. So we want to plot the domains of the moves on this graph. I will call n the total height of the tree, and at IC we are at height n minus 2. Next slide, please. So for B, we can plot, we know that there is n minus 2 layers, and we want to plot them along the direction k1, and we get those points, which each corresponds to one movement like this. Next slide. And we have something very similar for the integer that will go up. Next slide. And for the last, so C was decomposed into many movements, and in the end it looks like this triangle, because the first time we will need to move n-2 layers, and the next time n-1 until there is just one value to move. Next slide. So to characterize the dependency between moves, we need to know whether or not there is a conflict between them, and that we can know by analyzing the generated language, because you can see the rule with the k in the exponent as a star, as a regex, as a star in a regular expression, and we want to see whether the source or the destination can overlap, and if there is an overlap, we know there is a dependency between two moves. And that's kind of what we want to analyze. Next slide. So here, to summarize, each layer of the B subtree can be moved onto A, because A will be overwritten anyway. Next slide. We need the integer along the way. We need to move them in order because they are rewriting. They are overwriting the one just above them. So that's why there is a dependency between each integer. And we have kind of the same happening for the move over the layers. Next slide. So from this constraint, we want to derive a schedule, and this schedule should assign to each movement a date, which is positive. The schedule should be increasing. That is, that if a movement is dependent on another movement, we need to schedule one movement and the other after. And dates are not unique, because if two movements can be done at the same time, they could have the same date. Next slide. So here at this point, when we have written the equations for the dependencies, they are all linear inequations that can be given to an integral linear programming solver that will give us a solution, a schedule that is a solution of a schedule that will respect all the dependencies. So we get a graphic like on the left. That is, if we traverse all points with respect to lexicographic order, we are respecting the dependency that we expressed before. So basically, we have to, when we have this representation of a schedule, we have to go through each point by respecting the lexicographic order. Next slide. And next slide again. And so I want to explain how from this schedule representation we can produce some code. So here, as a first, the code generation algorithm works by projecting on the different coordinates. Next slide. So the first projection is on the I coordinates, and that will split the space in two. We will have the blue points on one side and all the other point on another side, and that kind of generates two loops, one for that will go from 0 to the kind of 0, and the other from 0 to 1, and the other one that will go from 1 to n minus 2. Next slide. After that, we are only interested in the subplane that is below, and we project on J, and that generates a loop over J. Next slide 2 times. And so we get the movement, all those movement in this loop. Next, we are doing the same process for the upper subplane. And next slide 2 times again. Yes. And in the end, we have all the points are done once. That is, all the movements that we wanted to schedule are done exactly once. On this slide, you can also see that we have simplified the fact that loops with only one loop, which will only when one time have been removed. And for simplicity's sake, I did not replace the movement by the real expression into C code, but in the end, it's only mem copies. So at this point, we have executable C code, and yeah. Next slide. So at this point, I've reached what we've presented in only in this part, which is a very oriented programming language, and starting from a high-level domain-specific language to generating code. And next slide. And currently, we are able to go from the transformation expressed as a pattern matching equation to C code, but we would like to extend the input language so that we would support recursion. That is, we can do operations on the node as we move them. That's not only memory movements, but also application of some function on them. And we would like to, so there is no need for recursion for that, but we would also like to be able to combine multiple values into one when we would do the memory movement. And until now, we do not exploit the fact that the generated code has parallel sections, and we would like to be able to use those soon. Next slide. So this part is more about our experiments concerning performances and what we have done on to see whether it's worsened. Yeah, I know I'm not very clear, but kind of yes.
Oh, maybe we should roll back to these pictures and listen to questions from the audience because it was this explanation was kind of fast. I basically a little bit lost when blue bullets has become not vertical but horizontal, and I no idea why.
Oh yes, I can re-explain that. There is no problem. But basically, you can interrupt me whenever you want. I do not mind. Um, the reason why the blue bullets change position is because here we have explained to the solver what the dependencies are, and when the solver maps k1 the direction k1 to direction j and maps direction k2 to direction I and k3 also to direction I. That and so if we traverse after the everything in lexicographical order, the layer of B will be moved um, like this. If we can move all the layer of B, after that we move an integer, so that's the that's the green point, and after we can move all the layers that are below, that are all those orange dots. And after you can go on to the other line, that is move an integer and move all the layers, but one less. I don't know if it's clear or not.
No, it is not.
Uh,
Maybe we should roll back to
maybe we
picture or
can go
something.
back to this picture. Thank you. So here, uh, the the dependencies between the each dot represent one memory movement, and here we are expressing a dependency between those memory movement with the arrows. And once we have all those dependencies expressed as linear inequations, we use a linear programming solver that will give us a scheduling which will respect all those dependencies. And what the solver did is that the direction k1 was mapped to the direction that was I on the other slide, and k2 was mapped to the direction j, and k3 was mapped to direction I think. But in
Where
the
where
end,
where can
yeah.
I find K1, K2, K3 in a tree picture?
Can you go on the slide before? Again. Here you can see in the rules there is here uh, k2 plus 2, k3, k2 plus 1, k3.
It is a levels kind of.
And we are instantiating k2, k3 um, between 0 and n minus 2. That's why, and that's how we generate the orange points. We try all the values of k2 um, that will produce a path on the right and on the left that gives a location in the tree. So, for
So
example, C0 is C0. The C0 is the value when K2 is equal to 0. That is, we go 2 times on the right, and we take the first node the node on the left. Sorry.
so C0 is the bottom blue bullet, yes?
C0 is the bottom orange bullet.
Uh-huh. So
If you go to
C1,
the slide just before, you have the blue and the green bullets as well.
Yeah, the blue bullets were done just two slides before.
That's the
Yes.
green one, and that's the blue ones.
Yes.
uh-huh.
So here we are instantiating K1 from 0 to n minus 2. And that's why it gives dots like this. And the K1, K2 corresponds to what is in the rule, yes. And basically we are plotting all the points that are valid, that is the path the path on the right and the path on the left gives a valid location in the tree.
So K3 is levels in the right subtree, right?
Yeah, K3 in the right subtree, yes.
So you are going from the top, from lower levels to.
Yeah, we go from the top, yes.
And you
Well,
don't
I
have
mean,
you don't have horizontal dependencies because I don't know, C1 overlaps with C0 by some
Yes,
reason.
C1 overlaps with
that's the
C0.
next thing, precisely. At this point, we don't have the dependencies yet. And the next slide, where we have the arrows, just a little bit, yes. Those are the dependencies. And you precisely do not have horizontal dependencies here because we don't need them. Because you're not rewriting, you're moving one layer to the left and up.
Yes. The movement that happens is that C0 is only one value and it will go just in the circle just above. Yes. C1 is two values and it will overwrite B0 that is one value and the other value will go into C0 because
Yeah,
C1
exactly.
is two values. Yes. And after C2 is four values and B1 is two values. So the half of C2 will go into B1 and the other half of C2 will go into C1.
So I got this idea from the tree representation, but it is kind of difficult to understand the arrows on the left. Okay, and back to original question, why blue bullets become horizontal? It's after some encoding to solver, yes?
Yes, that's because the variable were reordered when the solver solved the equations. That is, the blue dots are on K1 direction, and the K1 direction was mapped to what's called J direction on the left. Because K1, K2, and K3 are mapped to A and G. K1 is mapped to J, K2 is mapped to I, and K3 is mapped to I think.
Maybe the bigger picture is that on the left we have the various iteration variables that we discovered in the rules, but it doesn't really give us a concrete way to iterate through them in a way that satisfies the dependencies. It does not tell us, okay, you should try to iterate on K1 first and then K3. We don't know that yet. And so we can encode this problem into a integer linear programming problem through various means that we saw before. And after we give that to the solver, so an encoding of both the position and the dependencies, it gives us a way to walk through the iteration space in a way that respects the dependencies. And so it's just going to map some iteration variable to other directions, really. And then we can walk through them, in this case, in lexical order. So first I and then J.
No, it's first J and then I. Sorry.
First J and then I. Yeah, sure. Sorry. And so it's the fact that we encoded the problem using the encoding showed before assures us that the scheduling in question is correct, and that it's presumably it's a good schedule. We have other means of asserting that. But yes, it's a schedule that works.
And the reason we have 3 iteration variables on the right, on the left, on the left, is because at first we don't know how many iteration variables we need. So we prefer to have as many as we want in the first time, and after, when we schedule them, we try to find the minimum iteration variables. So here that's 2. Is it a bit clearer?
It is a little bit clear, yes. Maybe somebody else wants to ask a question.
Actually, I have a question. And do you have any theoretical description of what is expressible in this system? What transformations can be expressed in the what transformation cannot be expressed?
Technically, that's on the first slide of what Rukan can do, and we only accept algebraic data types. We don't want any sharing. The constructors have to be of fixed arities. And you can have the impression that we are always using the breadth first memory layout, but you don't need that at all. Maybe you can find something that's better for the data structure you're using, because what does our domain-specific language or all the computation after are only the computation of memory movements. So we have to move the memory that contains some values. But we only need a memory layout that from which it is easy to compute the children of a node. But for example, if you want to have a type with a list, we can do that. For example, trees with an unbounded number of children, we can do that.
Yeah, but the description is sort of language centric. So you fix some language and you say that everything which is expressed on this language you can implement. But my question was, is there some assessment of the power of this language? For example, if you have say like Pascal, we can encode any partial recursive function. If you move out the recursion and while loops from the Pascal, it will only capable to compute the primitive recursive function. So it's so I understand what language is, but do you have some assessment of which transformations in general terms can be encoded in this language? For example, if I want to implement list reversing, do I need to implement it in the language to make sure that it is possible to do? what if some transformation is not possible to express in your language? Is it possible to somewhere access it without attempts to implement non-implementable?
Can you repeat the very beginning of the question? What do you want it to? If you want to implement what?
List reversing, for example.
A list traversal.
Yes, list reverse. So, well, I assume that there are some transformations that cannot be expressed in this language.
But if we are just encoding a list, that will just be an array. And if we want to do a list traversal, that will just be the traversal of the array.
Yes, of course. But
yes.
I presume that there are some transformations which cannot be expressed in this language.
We can do transformation that will modify the memory that is used, because we are not augmenting the memory. So if you want to duplicate things, we can duplicate things.
I see. Okay, so it's.
To give a slightly higher level answers, this DSL is about modeling a new semantic for a construction that is similar to pattern matching, but that mutates in place. And it's like a pattern matching, really, in terms of semantic. It should be used as a tool in a bigger language. So evaluating the expressive power of just the construct itself is not very interesting in many ways, because you have a whole language around it. It's not ZDSL alone. It's a pattern matching construct in a language.
Yes.
But okay, there are some advanced systems of pattern matching, for example, for generalized algebraic types. So
you can see it as it's just a minimal language to observe, to evaluate how we can optimize pattern matching in a different ways with a different semantic as the usual one.
Okay. And,
yes, and it has to be embedded in some other language.
And my second question is, there is some rule for non-optimality in the implementation. So, is the synthesized program, generated program, is always optimal? Do you have an assessment of this quality?
So with the generation, if the schedule if the generated schedule is optimal, it depends on when you are when we use the solver, we can add other constraint if we want to maximize or minimize some parameters such as latency. If we want that as soon as a cell is ready, we want to fill it with another cell, we can express this with some linear constraint, and after and once the solver gives us a schedule, it is optimal with respect to those constraints, because that's just in the end that's only convex optimization, since that's a simplex algorithm.
Yeah. Okay.
So it depends on what you want to optimize. And I said that at the end, but currently we only produce sequential code, even though we know that we could generate parallel for loops. So even if we have the best schedule according to our equations, we still have room for improvements, at least on the parallel side.
Yeah, thank you. Does anybody else have questions or comments? Nobody else.
Okay, in that case, I
Yes.
will
Yeah.
continue.
Yes, please.
So this section is a bit different from what I presented before, and it's a bit more low level on, and gives some insight what were our original motivations. And so next slide, please. So I just remind what is an AVL tree, and that is a self-rebalancing binary search tree that is relying on a rotation mechanism to keep the balance. So here we have a tree that is not balanced, but if we rotate with y as the center, we can get a balanced tree. And what we saw is that if we use the memory layout that I presented before, that is, maybe it's clearer on next slide, please. Yes. The layers look like this in memory. And when you're performing the rotation, the layers are moves around in memory. And we have operations that very simple memory operations that can be composed in order to get the new T prime after the rotation. Next slide. And this then these operations are those two operations. The first one is a shift. So if we look at the tree on the left, there is I, and we will send it to AI, yes. And in the end, we get the tree on the left, on the right, sorry. Yes. And this is, you can do this in both directions, but yeah, that depends on whether you send the left or the right subtree. And pull up was what I used as the running example before, and pull down is the converse operation. That is, you create a blank node and you graft the tree just below. And pull down can be done in two directions, left or right, depending on if you choose to graft the tree on the left or on the right shield. Next slide. Yes.
This IA should be IB, right?
This I should be IB, yes.
Or this IB should be IA.
Yeah, I think it should be AB, yes.
Okay.
Yes. And it's moving around the subtrees in memory. And what is interesting is that we can express the rotations as compositions of those low-level operations. So, for example, the right rotation can be first we move down some subtree, we shift another one, fill up another one, and after we just have to move along X, Y, and Z so that the rotation is properly done. I should add a picture to show how it's done, but what is important is that you can decompose the rotations with those operations, and it's always the same order. It's first down, shift up and move values. And we wanted to see whether it was worse, because here we are moving onto a part of memory instead of just swapping pointers. Next slide. So we tried to see whether it was worse by having by benchmarking the implementation where the rotation are implemented with those memory movements, and another implementation that is normal AVLs. So the first step was we inserted randomly into both AVLs, so the one with the low-level transformation and the one with pointers. And we see that they are, on the first sensation, they are almost the same, even though one is only swapping pointers. On the dilation, we are much better than standard AVL with pointers. On the read process, it's also better, even though we use the breadth first layout. That means the breadth first layout is not optimal for searching into an array, because when you're performing a search, you're doing a depth first traversal. But still, we are better than the traditional implementation. And on the second insertion, we were a bit better. So what does it show is that even though this is not as optimal as what would allow us to do what I presented before, because here we have only 4 operations, and we have to the scheduling is not, it can't be finely tuned, because sometimes we have to finish a whole operation of moving a tree below. But when we move the tree below, we would some cells are cleared, and we could move all the other one in here. But here we have to finish one operation before we can do the next. And with what I presented before with the domain-specific language and the scheduling, we would have something that is much more fine-grained than those 4 operations. Next slide. And here it's just a benchmark to show that there is it could be interesting to parallelize some parts, because if you, according to the curves, it starts at very big size, so 2 to the 19th to be interesting. But as the size of the tree increases, we are better and better, since it's like 10 times faster in the end. And so this is this kind of curve explain why we would like to, in the end, produce parallel code for at the end of the automatic translation, because this is only manual experiments. Next slide. Yes. So here is just a summary of this part, that we have a simple decomposition of rotation into simpler operations. That's not as fine-grained that what we could have with the raw domain-specific language and all the tooling behind, but still we can achieve performance that are as good as a traditional pointer-based AVL. And there is even room for improvements if we use parallel code. And currently, I am working on making a complete parallel scenario, for example, the scenario with the database. But it's not completely done because there is some synchronization problem that kind of negates the improvement of the parallel version. So at this point, I have covered everything I wanted to cover. Yes, that's and the last part was essentially to show some performance on what if it's to give a bit of insight on the performance side. And the rest are just backup slides with some technical details if you want, but I don't think I will talk about them. So thank you very much. If you have any questions.
Thank you. So to summarize, I got the feeling that you are trying to build a language with algebraic data types where you abandon all ideas about persistence and sharing between different parts of trees, let's say trees, and you want to achieve the maximal optimal performance of mutation of
Yes.
algorithms that are doing in-place mutations, but which are implemented in the terms of the algebraic data types. And
Yes.
you want to use this approach in some, I don't know, experimental language maybe, or
experimental
hardware.
language, or when it will be more stable in maybe normal languages, because as another feature, because as of now it's just the domain-specific language to express data types and transformation on those data types. So alone it is not really interesting. It has to be embedded into a much bigger language as a feature.
Okay.
Alternatively, it could also be a way to implement some specific transformation, and we would emit the C code, for example, and the C code would be linked with a bigger library, and we would just emit a specialized piece of code that requires some transformation that are central and give good performance for them.
Something like Radanne generates, but not for data types, but for specific function definitions, maybe. Okay. Maybe there are something more questions from the audience. Otherwise, we should probably wrap it up. Okay, we should probably wrap it up. I'm pausing.